from Petra and then Favio. Both of them are PhD students in course groups at Max Planck Institute of Biochemistry. Yesterday, Petra gave us a very good talk about the Andromeda 1.0. Today, she will continue telling us about Andromeda 2.0. So, please.
Thank you very much for the introduction. So, as we already heard, we talked today about Andromeda 2.0, and I'm very happy to explain you the new developments on it. So, to remind you what we talked about yesterday, I again want to give you a brief overview. So we start again with a protein sample, which is then digested and subjected to LC-MS analysis. Then we have the experimental spectrum resulting, and then we try to identify this using the Andromeda database search engine, where theoretically, automatically generated theoretically spectra are matched against the experimental spectra. And then this match is called PSM, and the top scoring PSM identifies the experimental spectrum. So here I will explain you again how the conventional Andromeda score works. So as I explained yesterday, so we have two major branches. The first branch is the processing of the experimental MS spectra. So they are usually very large in size and complex. And to allow fast processing, we have to reduce the size. And I hope you all can remember how we do that. So first, if the raw file comes in profile mode, we try to we do centroiding. And if the resolution is high enough, we do de-isotoping. And then when we are able to detect the isotopic pattern, we can also transfer high charges to 1. And then as next, to even more reduce the complexity, we do intensity filtering, so the top Q peaks are picked per 100 Dalton window. And also maybe it's nice to know why we say 100 Dalton, because that's the average amino acid mass. So here it's called Q because we take different values from 12 down to 4, and then so we pick the most 12 intense peaks to the score calculation, and then we go down to 4 and also calculates the score, and then we pick the best score for this. So now let's have a look at the second branch again, where we generate the theoretical spectrum. And so here the main important information is the protein FASTA file, which contains the proteins which we expect in the sample. So here, because during the sample preparation step, we know the enzyme, so we know the cleavage positions, and therefore we can cut the protein into peptide sequences, and based on the information of the fragmentation method and the fixed and variable modification information, we can calculate the fragment masses in order to generate the theoretical spectra. So maybe because a few questions were asked yesterday about the number of variable modifications, so it's not limited to 10, so you also, if you have a need, you can increase the number, and it does not affect the statistics. So you don't identify additional false positives, that is all regulated by the FDR. It just really, when you offer the huge search space, it just takes very long. So as next, we have now the processed experimental spectra, and we generated the theoretical spectra. Again, we match those, and then we validate how good the identification is or the matching is based on the Andromeda score calculation. And then for this, two values are very important. So that is K, the number of matching ions between the theoretical and the experimental spectrum, and then also N, the total number of theoretical ions offered. And then when we have these two values, we feed them into the binomial probability-based calculation, where we calculate the probability of getting at least K matches by chance. Then this probability is multiplied by -10, the decadic logarithm, to get the final Andromeda score. Then, as I mentioned yesterday, we also do some score optimization. So once we offer neutral losses, once not, we see which score is better. Then we also do this with a different combination of ion series, like ETD, because that is a more complex mixture. And so, but talking about Andromeda 2.0, the main important parameter that we optimize is the top Q parameter. And so here, where we pick different values of Q, and yeah. So when we look now at this core calculation, we can see that the parameters that tell us most about the identification are the number of matching ions and the total number. But however, when we look at the spectra, there are more information available that helps to increase the identification rate. So which features they are and how we can use them into the score, I will tell you now in form of Andromeda 2.0. So Andromeda 2.0 supports two novel scoring methods. The first one is the tag-enhanced scoring, and the second one is the symmetric binomial probability-based scoring, which uses intensities predicted by deep learning algorithms and conventional machine learning algorithms for the theoretical spectrum. So now I will go into detail into those. So let's first start with the tag-enhanced scoring method. So what is the idea behind this? So as we know, we look at the number of matching peaks. But with this scoring method, we don't only look at the number of matching peaks, but also at the number of neighboring matching peaks within an ion series. And why is this important? So here, as an example, we have an experimental spectrum and then a theoretical spectrum. And here we have consecutively matching peaks within an ion series. And this gives us a higher probability that for this region, the identified amino acid sequence is the correct one, since the distance between two neighboring peaks within an ion series should be the mass of an amino acid. So here another example. So we have here again the experimental spectrum, then two possible theoretical spectrum explaining this. And we can see we have the total number of theoretical ions in the spectra, so the n value and the k value is the same, so both have 6 matching peaks. So we would end up having the same score for those, but we know that the consecutively matching spectra is more likely to be the correct one. So the next question is how we include this information into the score calculation, and this is done the following way. So we see here the Andromeda score calculation, the values we know already, and to include the neighboring information, we have to modify our k. And this is split into 3 values. And so once we offer the k0, which is the number of matching peaks without any serious neighbors matching, and this value is then multiplied by a weight. In this case, A0. And then as K1, we have the number of matching peaks with just 1 serious neighbors matching, also multiplied by a weight. And K2 is the number of matching peaks with 2 serious neighbors matching. And then in the end, we sum up the weighted K values and calculate the score again. So as next, we applied the scoring method to HLA dataset. And this scoring method is especially promising for this kind of data because it's very complex and you have a huge search space due to the undefined enzyme cleavage specificity and also the low quality spectra. So we are hoping that we get an improvement, which we already can see here that we get. So the HLA dataset was analyzed using different fragmentation methods. And so we analyzed them using MaxQuant. We set unspecific digestion, 1% protein and PSM FDR, and then we also optimized the weights for the K values. Then we did the analysis and compared the tag-enhanced scoring to the conventional Andromeda scoring, so seen here. And we can see that for all of the fragmentation methods, we could increase the number of identified PSMs significantly. So for CID, we could gain 13.5% more identifications, for HCD 15%, and for ETD 4.6%. However, for ETD, it was kind of expected that it doesn't improve much because the fragmentation on the peptide is more complex. Then let's move on to the symmetric binomial probability-based scoring calculation. So it does use the predicted intensities based on machine learning approaches for the theoretical spectra. And the intensity information in MS2 spectra is highly informative, and therefore it should help to find the correct PSM for the experimental spectra. So despite that fact, not a lot or none of the database search engine makes use of this information. And in Andromeda, we use already the intensity information, but only to give higher weights to high intense peaks, matches to high intense peaks. But it does not use in any sense if a peak is expected to be highly intense based on the sequence context. So with Andromeda 2.0, we want to include this information into the scoring, and now I want to show you how it's done. So here we see again the formula to calculate the Andromeda score. And what is different here? So because we predict the intensity for the theoretical spectra, we are able to do the same thing with the top Q value, what we did at the experimental spectrum side. So we sort first the peaks by intensities, and then we pick different values for most intense peaks, as we did for the Q value optimization. And the same we can do now with the intensity information on the theoretical spectrum side. So we start first offering all theoretical ions in the theoretical spectra and see how many are matching, and this is also the conventional Andromeda score. So this is still included in this version, and then we offer 13, 10, and different numbers. So also here we have an example where we initially offered 5, and then we see 3 are matching, and then we offer 3, and then 3 are matching out of this, and yeah. So also in the scoring, the binomial probability-based scoring takes into account that when you offer a lot, you would expect that a lot are matching, and then you offer less, and then still a lot are matching. That, of course, gives a much better score. Then here also an example to make this a bit more clear. So here we have the example of the experimental spectrum and 2 theoretical spectra matching against this, and we would see here, without the intensity information, no difference that the first spectrum has high intense peaks matching and the second one peaks to lower intense peaks. And with the intensity predictions, we can make this more clear that the matches are happening to higher intense ones. And why is the intensity important? So as I said, we have the sequence information, and sometimes when you have a combination of some amino acids, so with proline it rarely fragments, so you have a lower intensities, but if you have another combination of amino acids which is more likely to fragment, you have a higher intensity, and therefore you can include this into the scoring. And here, like an example, so when we have now, we offer different values of theoretical spectra and see how many are matching. We can see when we offer 5, for the first one we have 3 matches, and here just 1 match. So this really helps. And now we applied the scoring method to a synthetic data set from Proteome tools, Proteome tools data set from the Crystal Lab, and here we can see that with the conventional Andromeda score, the correct PSM was not the top scoring PSM, and then it became the top scoring PSM when the intensity-informed Andromeda score was used. And here is especially a very nice example because here the amino acid sequence was before in the wrong order and were put in the correct order using the intensity-informed Andromeda score. Here is another example where a complete different PSM became the top scoring which is the correct one, and it became the top scoring PSM when the intensity-informed Andromeda score was used. And also we can see here that the matches are now to higher intense peaks. Then we also applied this new scoring method to a more complex biological data set, and here we analyzed a HeLa data set. And for simplifying the interpretation, we did not apply a protein FDR, but we set 1% PSM FDR, and then we scanned different Q values, and then we can see that for the whole region of Q values, the intensity-informed Andromeda score performs better than the conventional Andromeda score, and especially in the high specific region, we can see that the difference between those results identification rate is largest. Then now the interesting questions, where do we get the intensity predictions from? And for this we developed in cooperation with Verily 2 machine learning approaches. So the first one is deep mass prism, which is based on recurrent neural network and bidirectional recurrent neural network, but more we will hear about that by Peter tomorrow in his talk. And then we also developed Winner, which is based on a sliding window approach using conventional machine learning. So where does the name come from? Because it's a sliding window approach and it's based on neuronal network, and this makes it easy retrainable. So the advantage of Winner is here that it's less computational expensive, and this allows ad hoc model generation, and this is especially important when you are working on specific data sets, which needs, again, retraining. And both models predict intensities for peptides of any length. And then we compared these 2 models against the state-of-the-art tool, which is MS2PIP. And for this, for deep mass prism was analyzed or trained on 25 datasets, 5 datasets per 5 organisms. And the Windows-based approach was, so Winner was trained on the Proteome tools dataset, but both datasets were treated the similar way for the data analysis. So we analyzed them with MaxQuant, we applied 1% FDR for proteins and PSMs, and then for the result, we just took the unique peptides, which have a score above 100, and then those unique peptides were split in a ratio to 95:5 for training, testing, and validation. And then, so we compared the results of these 2 approaches, and also the theoretical limit was calculated, which is the reproducibility of technical replicates. And so we can see here that deep mass prism nearly reaches this theoretical limit, and also nearly Winner, and all of them are outperforming MS2PIP. And to give you a brief summary, what is done here, so we successfully developed 2 novel scoring methods, the tag-enhanced scoring and the symmetric binomial probability-based scoring. And then we also successfully developed 2 prediction models, the deep mass prism, which can be used for the general data set. It allows very accurate prediction of the intensities, and then Winner, which allows fast retraining for specific data sets. And they both are now being integrated into MaxQuant. And as next steps, so at the moment, they provide predictions for Yeah, for CID and HCD and neutral losses. And the next step would be to provide also predictions for PTMs and for non-tryptic peptides. And we also would like to support other fragmentation methods like ETD and ETHCD. And with next, I want to ask Favio to come to keep talking.
No, it's which.
And thank you for your attention.
Thank you, Petra. Thank you, Petra, again, and good morning, everybody. Now I'm going to speak about Winner, but before speaking about Winner, I want to take 1 or 2 minutes to talk about MS2PIP. So MS2PIP is a tool for peptide intensity predictions. It predicts for fragmentation methods CID and HCD, and for peptides with charge +2 and charge +3. It can predict the algorithm that they are using is the random forest, and it predicts intensities for peptides the length of 80 to 24. The feature vector, or in other ways, what they consider it's important for the prediction is like the chemical properties of the peptide. As Petra said, we benchmark a Winner and the mass against MS2PIP. MS2PIP has 2 publications, the first one 2013 and the second 2015. The second is just out of date and an improvement of the first version. So just I want to give you like an overview how is the predictions in MS2PIP. So for MS2PIP, you have to provide a list of sequence. And for in this list of sequence, you have to show, you have to provide the sequence, of course, and the fragmentation method and the charge. The only thing that you have to do is to look for the corresponding model according to the peptide length, and then you get the predicted intensities. So you can see that here is nothing wrong with this. In fact, this method is called like assemble when we are talking in machine learning. So you divide your problem, you have many like models, and you make a prediction. But for us, this is a problem because we want to implement this in Max 1, and we want like to give to the users the possibility that they train the model. So it has to be something easy to train. And just imagine if they have so much models to train, it's going to be so difficult. So how we solve the problem of predicting different peptide lengths? We came with winners, so it has 2 goals. As we don't want to have restrictions in the peptide length. And also, we want to reduce as minimum the number of models. So here, so we came with the idea of a sliding window approach. So just imagine you have here your peptide. This peptide, it has the length of 7. We have the Y ions that goes from 1 to 6, and the B ions that here in this case only we have 3 B ions. So the second step is we define our window size. So window size, no, sorry, but, I want to show something else. Here, just remember that here the amino acid A is attached to the N-terminal, and the amino acid T is attached to the C-terminal. And something else important here is that you can see here that the largest peak here is a Y6. So what we do is a normalization between Y and B ions, and we take as 1 like the highest peak. So after normalization, you will have something like looks like this one. Everything is normalized. And now is what I was saying, we have to define our window size. So our window size here, just for this example, is size 2. So what we have here is the targeted bond. So the targeted bond, first we will use this for training our model, machine learning model, and later for predictions. So when we say window size 2, we have 2 amino acids to the left, and we have 2 amino acids to the right. So how we do this? We just focus in the first bond of the peptide, and here we can see like some notation. So we start to build our future metrics. So you can see here that in the position Si -2, we don't have any amino acid. So when we don't have an amino acid, we just write empty space. In the position Si -1, we have the amino acid A. Here in the right side position Si plus 1, we have the amino acid P, and in the position Si plus 2, we have the amino acid N. Which is the first amino acid of the peptide? Is the amino acid A, and which is the amino acid at the C-terminal? Is the amino acid T. So what is the distance of this bond to the N-terminal? Is 1, and what is the distance of this bond to the C-terminal? Is 6. The complete length, as I said before, of this one is the peptide 7. And in this case, what we want is that the machine learns to predict Y and B ions. So here we are targeting, and we are saying that the value for Y is 1.0, and the value for B ions is 0.6. You have to remember that what I'm explaining right now is how we train the model. So we do this for the next bond. And just one more time, so it's really clear. What we have on the left, so we have the amino acid A, we have the amino acid P. In the position Si plus 1, we have the amino acid N, and in position Si plus 2, we have the amino acid R. Something that is not going to change for peptide is the amino acid at the N-terminal and the amino acid at the C-terminal, A and T. In here, the distance changed because the distance to the N-terminal is 2, and the distance to this bond to the C-terminal is 5. The length also doesn't change. Here we're saying to the machine learning, okay, you have to learn that this is the value of 0.4 for Y ions, and here you can see that we don't have B ions. So when we don't have B ions, we just write 0. We do this procedure until we reach the last bond. So one last time we have this last bond, and we can see that on the left we have the amino acid T, the amino acid E, in the position Si plus 1, the amino acid T, and here again we have an empty space, so we just write empty. What it remains exactly the same is the amino acid at the N and C terminal. The distance here is like 6 to the C-terminal and 1 to the N-terminal. There is a typo here. And the Y ion 0.5, and the B ion has the value of 0. So you might ask, which is the correct window size? And it might be like just 1, maybe just 2, or like the example that I showed before, or 4. So at the end of this presentation, I will going to show you which is the correct window size, but just until that, just make a guess. And then I want to talk about some like words that you have to know in machine learning. So what you are using for training in machine learning is called feature matrix. So the rows are called features vectors, and what you are targeting in order to predict is called targets. So last time, the feature vector that we built, it was based on in this window size. We took amino acids on the left, amino acids on the right. We have the amino acid and the N and C terminal, also the distance of the bond to this N and C terminal, and the length of the sequence. Something that is also really important when you are training something in machine learning is that machines don't recognize like categorical values. They don't recognize like the amino acid letters. So what we did here is one-hot encoding. So we choose like a vector, a binary vector, that is the length of 21. Why 21? Because we have like 20 amino acids plus the empty space. So just imagine we replace the amino acid A with 20 zeros, and then the value of 1. For the amino acid P, 6 zeros, and the second last value is 1. And for empty space, 1s and 20 zeros. You remember that the first step that I did, or that we did, it was just to normalize everything to 0 and 1. Once that we had these values normalized, we applied a transformation, a block transformation. What we did this because for machine learning, it's like sometimes when you apply these log transformations, machines can learn faster and converge to the solution faster. We did this for Y and B ions. So here in this like feature matrix, what I want to show you with different colors is that this will correspond to one peptide, this to another peptide, and this to another peptide. So Here we didn't normalize like the length of the sequence and also the distance, right? So what we have to do is also to normalize that to 0 to 1, and just we divide by the maximum length of the sequence that we find in this list of peptides. But in fact, we will not have values that are 0 because we don't have a peptides of length of 0, or the same happens with the distance. It's just the values above 0 and until we reach 1. So the data set that we use is proteomic tools. And here, like the first version of this one, they are focused just in peptides. They have 1,460 LC-MS runs. And it's synthetic peptides, so what it can be best for training. So what we did is we copy all the information. So what we did is copy all the information of the proteomic tools to one database, MySQL database. And what we did is apply two filters. The first filter, it was just to take the fragmentations CID and HCD and the charges +2 and +3. Why we did this one? Because it's the same like fragmentation methods and charge that MS2P took in account. So we want to compare models. The second filter that we did, it was we wanted to have for each sequence unique spectra. So what we did is we took the spectra with maximum Andromeda score. So once that we have our list of a sequence and Andromeda score, we remove all the sequence that had Andromeda score below 100. So with this, we built a really confident data set for training. So here you can see that we have different number of peptides depending on the fragmentation method and the charge. And once that we have the list of peptides, we generate our future vectors with the sliding window approach, like I explained with this sliding approach. So for each model, we divide in training, testing, and validation with the ratios of 90-5-5. And we use 3 machine learnings, conventional machine learning algorithms. The first one was support vector regression. The second one was random forest. And the third one was neural networks. So why we tried first with support vector regression. Support vector regression has really good performance in high dimensional spaces. We use one kernel that is RVF kernel, and when you use this kernel, you have to play with 2 parameters. Something that is a downside for support vector regressions is that they have a limitation in the training size. They only you can only train around 100,000 data points. For random forest, it really depends what kind of problem you are trying to solve. But sometimes they have lower performance than support vector regression of support vector machines. But they have a little bit more of parameters that you have to tune, around 5 or 6. It really depends if you are training this with R or Python. But good thing is that you can just set this parameters by default, and it will predict really good. Also with random forest, we don't have a training size limitation. And the last one, neural networks, they are really good when we want to solve high complex problems. You have more parameters that you have to tune. Sometimes it's a bit difficult, but it's worth it to do it. We don't have training size limitations. In fact, neural networks perform really good. The more data that you have, it will perform much better. And something that is really good here is in neural networks, we can have multiple outputs. So when I talk about support vector regression and random forest, you have to build one model for one target. So in this case, you remember that we have 2 targets. It was ions Y and B. So in fact, we had to build one model to predict Y ions, one model to predict B ions, and then combine, right? But with neural networks, we don't have this problem. We can have multiple outputs. About time, for each model, it was, for support vector regression, it was 11 hours. Random forest, it's quite fast, it's 1 hour. And neural networks, it was around 2 hours. you know that our goal is to put this in Max1, so we are also taking into account how much time it takes these ones. And here are the results. This is the Pearson correlation, and these are models. The first is super vector regression. The second one is random forest. And this is the random forest plus super vector regression. This is just, we combine, this is, like I said before, assemble algorithms. So you combine the predicted intensity for random forest, the predicted intensity for super vector regression, just sum up both and divide by 2. And it's just the mean. But even you can see, doing so many things for this one, we cannot defeat the results of neural networks that it was performing really good for the model CID plus 2. Here, you remember about the window size, right? So the correct answer when we stopped our training, it was when we took like window size 24. So you can see here that we were trying all the window size possibles, always like taking even numbers. And you can see here that the difference between window size 16 and 24 is just a slight difference, almost like the same median and same median, and also same variability. This is the results of winner versus MS2PIP. You can see that we outperform in the 4 models. And we are doing even really good in HCD plus 3 where MS2P was not doing really good. I want to say thank you to Jürgen, to the Cox Lab group, and especially to Peter for all the collaboration. And if you have questions, and Shivani, of course. Thank you, Shivani.
Any questions?
Yeah, I have one question for you. It's about the hot encoding of 20 plus 1, 20 amino acids. Do you think it's worth expanding to 22 plus 1, meaning also the other 2 genetically encoded, like the selenocysteine and the pyrrolysine? Because there's not much information there in terms of mass spec, so anything that could come with, some mass spec evidence of those peptides. The only one that I was able to find was in Global Proteome Machine Database. So do you think it's worth expanding that?
It really depends. So this is just the first version, and it really depends. Later, for example, we will have like one hot encoding for modifications and so on. So it really depends what kind of problem you are trying to solve. So if, for example, we have modifications, we will have one hot encoding that is larger because we will like take in account like PTMs. So it really depends.
Yeah, because these 2 amino acids, they are not much widespread, but certainly they are there. The pyrrolysine is in the bacterial world, and the selenocysteine is a little bit more widespread, but they are there. So probably
maybe it's worth it to try it.
Okay. Thanks.
More questions?
Hi. So, nice presentation. Will you have to retrain the algorithm for each and every data set?
Yes, that is the goal. So we have 2 models. The model that is with like in deep learning will explain Peter. This model we don't retrain, so we will have like many data sets. But when you have like a really specific data set that you just want to train, you use our approach that is winner. But we will provide like many like predefined predicted data sets.
I got a question concerning the architecture of the neural network. So how many hidden layers do you have and how many neurons? Can you say something about that?
Yes, for almost all the models, it was just like 2 hidden layers and around 500 neurons for each layer.
So I have 2 questions. One for Petra. So with the tag-enhanced scoring method as well as the symmetric binomial probability score, so is Max1 the only one that is implementing these, or are there other search engines that are already doing that?
So for the symmetric one, as far as I'm aware of, that's the only one. And also from the, where you look at the neighbors in that way as we do. So
Okay, so Muxpond is the only one at the moment. So nothing else, Proteome Discoverer or Peaks, none of them are doing this actually.
not that I'm aware of.
Okay.
So.
Okay, if there's no any questions, let's thank the speakers. Thanks, Favio and Petra.